Hello, in this video we're going to see how to solve first-order linear differential equations. So let's see how these equations look like to begin with. So I'll write over here, and I'm saying it's first-order differential equation, so we are going to have the derivative of a function with respect to the variable, but only the first derivative. So let's say we have dy dx plus, and then we are going to have the function itself, y, could be multiplied by some function of x. So p of x plus y times y, and this is going to be equal to some function of x I'm calling q. So this is how first order linear differential equations look like, and when you're given one, you may have to rearrange it to look that way. I'm going to try to give you an idea of what is it that we want to do. The idea is the following. What we have in the left hand side somehow looks or could look with a little bit of modification, like the result of applying the product rule to, let's say, something, we don't know what that something is, times the function y. So the derivative of some function times y. So if we take that derivative by the product rule, we'll have the derivative of the first function, whatever that is, times y, plus that function, whatever it is, times the derivative of y with respect to x. Okay, let me change the order of the terms actually, because we have something like this actually in our original equation. We do have the dy dx part, that's over here, and then we have something multiplying the y, we have the y over there. So what we would like to have is a function that we can complete over here. So when we take the derivative with the product rule, we get our equation, or well, something multiplying our equation. So let me go one step further with this idea. Let's say we multiply our original equation by some function I of x on both sides. So we have I of x times the derivative of y with respect to x plus I of x times p of x times y is going to be equal to I of x times q of x. So now this is starting to look a little bit more like the equation with the product rule over here. For that to be true, what we will need is the product of I of x times p of x to be the same as the derivative of the function we are looking for, and then the function I of x, well, that's a function that I call dot 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 and my product rule above. So what we are saying is that we want the function I of x to have the property that when we take its derivative, the result is I of x times p of x. So if you look over here, actually what we have is that the function I of x we want to find has to verify a differential equation. What we wrote over here, this, it's actually a differential equation, and it's a separable one, since we can write it in the form, well, this is the function we're trying to find, I, so the function of the function we're trying to find is just the identity times some function of x. So we are going to solve this because we know how to solve separable differential equations. We are going to write that 1 over I times I prime of x is the same as p of x. And then we want to consider the integral of this with respect to x on both sides. So I'm going to write integral over here. I'm going to need to move to make a little bit of space here. So the integral of 1 over I times I prime of x dx is equal to the integral of p of x dx. We can do a change of variable here. if u is the function I, is a function of x, I of x, then du is going to be I prime dx. So actually what we have on the left-hand side is just the integral of 1 over u du, and on the right-hand side we have the integral of p of x dx. We can't really solve the right-hand side because we don't know what the function p is, but we can solve the left-hand side because the antiderivative of 1 over u is the natural logarithm of u, and actually that means that's the natural logarithm of I. So making a little bit of space over here, what I'm saying is that the function I of x is given by the exponential of any antiderivative of p of x with respect to x. So that's a function we want to find. Let's check that that function does the trick that we want. We need a little bit more space. And also let me tell you that that function I of x is what we call the integrating factor. So going back to our differential equation, we had dy dx plus p of x times y is equal to q of x. And we are going to multiply both sides by the integrating factor. So expanding and writing what the integrating factor actually is, we have the integrating factor times the derivative of y with respect to x plus the integrating factor times the function p times y, and then on the other side q of x times the integrating factor. Over there we don't really need to see what it is, so I keep writing I just to make it short. So on the left hand side, this is what we have, the result of applying the product rule. So if we have e to the power of p of x dx, our integrating factors times y, and we take the derivative, we get what we have on the left-hand side. But let's check this because we need to convince ourselves of this. This is the key point of the method. So if we apply that product rule, the order of the terms doesn't matter. So let me write first the derivative of y's part. So we're gonna have the integrating factor times the derivative of y with respect to x plus the derivative of the integrating factor times y. And this is equal to, I'm gonna leave the first term as it is because that's what we want actually, that's ready for us. Plus, and then if I want to take the derivative of the exponential function, I'm going to get the exponential function itself times the derivative of the function I'm exponenting. So the derivative of the integral of p of x, so that's p of x times y. So we checked that it's true that what we have on the left-hand side is actually what we want. So I'm going to erase this part just to have space to finish the reasoning, because once we are convinced that the left-hand side is what we want, then we are saying that this is equal to q of x times the integrating factor. So we are going to consider the antiderivative of both sides with respect to x. So on the left-hand side, we have the derivative with respect to x and then the antiderivative. So that's like not doing anything. So what we have is the integrating factor times y is equal to some integral that we hope we would be able to find. If we are able to find that antiderivative on the right-hand side, then we can isolate y and we'll be done solving our differential equation. Now you may be wondering, do we have to do this again each time we are trying to solve a first-order linear differential equation? And the answer is no, you don't need to do all this again. This video so far have shown you what the method is and why it works, but your focus is going to be on finding the integrating factor, defined as it is over here, and then multiplying both sides by the integrating factor. Let's see an example how I will solve it. I wrote over here the steps that we're going to follow and the differential equation that we are going to solve. First of all, we want to check that this is a linear first order differential equation, and you can see that it is, and we want to write it in the standard form that we described at the beginning of the video. So we want to make sure that on the right hand side we only have a function of x. This means in this case I'm going to need to write dy dx plus 3x squared times y is equal to 6x squared. So we need to identify what is the function q of p of x and q of x in this case. This 3x squared is our p of x, and on the other side of the equality we have q of x. We need to find now what is the integrating factor. So I of x is going to be an antiderivative of the function p of x, the exponential function of that, so e to the power of antiderivative of 3x squared dx. This is, well, the function x cubed has derivative 3x squared, so e to the x cubed is going to be our integrating factor. We now need to multiply our differential equation by the integrating factor. So I'm going to write e to the power of x cubed times dy dx plus e to the power of x cubed times 3x squared times y is equal to e to the power of x cubed times 6x squared. We write the left-hand side as the integrating factor times y, all of that prime. So in this case, we are going to have e to the power of x cubed times y prime. And you should check for yourself that this is really what we have on the left-hand side, because this is what makes the method work. So one of the terms is going to have the same exponential times the derivative of y with respect to x, and on the other one we have to have y multiplied by the derivative of e to the power of x cubed, and the result of applying the chain rule to that is, in fact, e to the power of x cubed times 3x squared. So we know our work so far is correct. Now we are going to find the antiderivatives on both sides with respect to x, so we're integrating both sides. So on the left-hand side, when we integrate with respect to x, the derivative cancels out, so we have e to the x cubed times y is equal to the antiderivative of e to the x cubed times 6x squared dx. We need to find this antiderivative, and we can maybe take 2 outside the integral, so we have 2 times e to the x cubed times 3x squared dx, and that's, well, we already had something like this before. We know that the antiderivative of this is going to be e to the x cubed, and we have the 2 multiplied, and we need to write a constant. If we do not write the constant, then this is not going to work. Let's isolate y, and then we'll talk about the constant again. So y is going to be, we have e to the power of something to divide on in both sides. So y is going to be equal to 2e to the x cubed plus c over e to the x cubed. So that means we are getting 2 plus c times e to the minus x cubed. So notice that over here, so this result for y is a family of functions. If we did not write the constant, then we'll end up only with the constant solution 2, and that's obviously not all the possible solutions we have over here. But you may want to check that this is in fact a family of solutions that solve the original differential equation.